Hey, what's up, guys? This is Chung here again. So this time, 1856 maximum subarray minimum product. Okay, so a minimum product of an array is equal to the minimum value in the array, right? Multiplied by the array sum. So for example, the array is this one, right? The minimum value is 2, and the sum is 10. That's why the mean product of this one is 2 times 10 equals to 20, right? Pretty easy, right? But then it asks us to do this. We need to find the maximum mean product of all the possible subarrays. Okay, and then return the modular of this one. So this is just like a small thing, right? He asks us to maximize the mean product before doing this kind of modular, right? So, and the constraint is 10 to the power of 5. So clearly, I mean, the brute force way will be we just enumerate, we traverse, we find all the possible subarrays, right? And for each of the subarrays, we can do a random sum, and then we can also get the minimum value of that subarray, right? And then we can compare the result for all subarrays. But given this 10 to the power of 5 constraints, to find all the subarrays, it's going to be O of n squared times complexity, right? That would definitely TLE. So how can we solve it, right? This one actually, it's super similar as a very early problem. It's called, I think it's number 84. It's called a maximum area, maximum rectangle area for the histogram. And this one is not exactly, almost 95% the same. Unless, for that histogram, you're given like a different histogram, right? I mean, along on the here, right? Something like this, right? And each histogram has like a height, right? And it asks us to find basically the minimum rectangle area of the histogram. Let's say, for example, if we want to find the minimum area, there could be basically each rectangle is the same as a subarray here, because we could have like different combinations of the starting point and ending point. So here, and if we fix the starting point and ending point, right? So the width is fixed, but the height is what? The height is exactly the minimum value of all the numbers here, right? That's why the height in this one is like the height is the minimum height, and in this case, it's actually the minimum number in this case, and the width in this case is the width. This is height. This is width. The width is the index, the absolute difference of index. But in our case, it's a sum. It's a sum of the of the numbers in the array. So, okay, with that being said, right, even though they're similar, we still have to figure out how to solve this one, right? And how can we solve it? I mean, the way we're solving it is that I believe I will also uploaded that videos for that 84 histogram problem. You guys can also check that out. But for this one, the way we're solving this, is the basically at each of the number here, we're trying to fix. Basically, we're trying, for each of the numbers, we're assuming that that number is the minimum value. Is the minimum value among the in that subarray. Okay, and if we know that, right, then we can simply use this number to times the that sum. But how can we quickly find the basically the left and the right boundaries for this subarray who has this number as the smallest number? So and to find that, like I said, we need two boundaries, the left one and the right one. So the way we're doing this, we're gonna use like a monotonic queue here. Monotonic stack here, which in this case is gonna be a increasing monotonic stack. And how does it work? Oh, so since it's increasing, right? So let's say we have uh, 3, 5, 6, right? We have 3, 5, 6, and then we have 4 here. So the monotonic queue, right? So in the monotonic queue, we store the index, okay, inside of the value here, because we need that index to help us find the sum for that range. So we have like 4 here, right? So whenever this 4 comes in here, there's like 4 here. If the new number is greater than the last one, we simply append this one to the monotonic stack here. Otherwise, if this one is smaller than the previous one, what does it mean? It means that we can basically check this number as the minimum value. And why is that? Because since the current number is smaller than the 6, we know the range for the range of the subarray who has 6 as a minimum value is what? Is the right boundaries is already defined, which is the 4 here. Which is 4. This is the right boundaries. And the only thing left is that how can we find the left boundaries? Right. So this is because the ones on the left next to the priority queue, right? Sorry, not priority queue. Next to the monotonic stack here will be, because this one is increasing. That's why this one is definitely smaller than 6, right? That's why the left boundary is here. Is this one. Now with this kind of left and right boundaries, right? We can easily find the sum. The sum of the array who has this 6 as a minimum value. We can use like a pre-sum to quickly calculate the sum, right, within the range. Yeah, and why do we so a little bit more about this. So why we use the index for 4 to be the right boundary and instead of 6, because we could have like another 6 here. We could have like another 6 here. Okay, and there's also could be some another 6 here. So that's why when the 4 comes in, so when the 4 comes in, first we'll pop out this 6, right? And then when we're popping out this 6 here, the right boundary is still 4, because here they are all the range, they are all the same, right? Yeah, and we are trying to basically with a fixed a smallest number here, we're trying to get the biggest the longest subarray possible, right? That's why in this case the right boundary should be the right the index of this 4 here. And regarding the left boundaries, so we could have another 6 here, right? So actually, this left boundary is not as accurate as the right boundaries because since we'll be using this index for the on the top one of the priority queue, right? So if we pop this one here, if we pop this 6 out, basically we'll be using the index for this one. Then we're saying, okay, the left boundary stop before this one here. But in reality, actually, this one is also part of the subarray. But it's not a problem because after popping this 6 out, we'll also be popping this 6 out. And when we pop this 6 out, when we process this 6, we'll have the correct left and right boundary. Right? And why the left boundary works, this is because, let's say we have 3, 5, and then let's say we have 7 somewhere here, right? And then we have a 6, 6, 6, and then 4. That's why, the 7 is like, is right in the middle, right? And that's why we know, okay, so when we process 6 here, if we pick 6, so what's the correct left and right boundary, right? So this is the left, and this is the right. And what's in the middle are the biggest, are the longest subarray who has the 6 as the minimum value. That's why, by using this kind of monotonic stack here, increasing stack here, we can quickly find the left and the right boundary given a fix by fixing a minimum value. Yeah, I mean, I also talk about this concept in my 84 problem videos. Instead for that one, instead of using the number here, I use like a histogram because that's a histogram problem, right? To explain this idea here. Cool. So let's start coding then. Enough explaining. Okay, so let's see what else. And and to simplify the code here, we can add like nums this to the -1. The reason being is that we could have something, so based on our logic here, let's say we have 3, 5, 7, 6, 6, 6, and 4, right? So if we will only process by having like a smaller number than the previous one in the monotonic stack, right? So which means that in this, when 4 comes in, this thing will be gone, and then we'll be having 3 and 4 left in that monotonic stack, and we also need to fix that part. Not fix, try to process the remaining one. Okay. And so this part, in order to do that, we can simply add like a -1 to the end of the num, so that we'll always have a -1 in the end, and the -1 will always be smaller than the previous one, right? That's why we can fix the last scenario, and then we're gonna have like a pre-sum equals to 0. For this pre-sum here, someone prefer to start from 0, and then we have like 1, 3, 5, 7, so on and so forth. For me personally, I prefer having like this dictionary and to populate -1, so that I don't have to shift the index to the right by 1 when it comes to use the prefix sum. I mean, either way works fine. I mean, it's just like matter of your how you how you will think of this pre-sum like index, right? So that's why we have this one, enumerate nums, okay? And the pre-sum I equals the pre-sum of I -1 dot sum. I do this so that when I is equal to 0, we have a value, or someone add like a 0, prefix like a 0 to the pre-sum array here, so that they can do a I +1. they do a I minus 1, they will also be okay. And then the n is the length of the nums, right? And then we have an increasing q, right? At the beginning, it's going to be a minus 1. So the reason we do a minus 1 here is also because we want to make sure, there's always a like item in this queue here, because we'll be using the value in this queue as our left boundary. That's why we have to have like a minus 1 here. So if the answer is equal to 0, and then for the right boundaries, so for the right boundary, it's going to be a number in the enumerate nums, right? And let's maintain this monotonic queue first. So if while the actually it's not a queue. I keep saying queue. It's a stack. Monotonic stack. The increasing stack actually. If this one is not equals to the minus 1, right, and the number is smaller than the nums of the increasing stack of minus 1, right? So like I said, if the current one is smaller than the first one in the monotonic stack here, we know that okay, we have find the right boundary for this number. And that's why we need to calculate the result for this number, and by finding the left boundaries. So that's why we have a current minimum number. I'll use a current minimum to be the minimum number of its and the minimum number is this one. It's the numbers of the increasing stack dot pop, because we're storing, instead of storing the values, we're storing the index. Like I said, because we could have like multiple 6. That's why since we need to get the summary, the sum of the range sum. That's why we use the index instead of the value itself. And so we already have this current minimum number for the range, for the array, right? Now let's find the left boundary. So the left boundary is what? It's the increasing stack minus 1. Like I said, it's the one that's left, because we know the one that's left on the left in the increasing stack will be smaller, either equal or smaller than the current one. Okay, that's why we use the range sum, the left boundary. Now for the sum, this is the right boundary, and this is the left boundary. Okay. So there's a little bit off here, because if we use the pre-sum in this way, let's say we're trying to get like the pre-sum in the left to right. So what's going to be the way we're getting it? So if we get trying the left and the right, right? So the sum between this one, between the left and right, is the pre-sum of right, minus the pre-sum of L minus 1. That's how this pre-sum works. Basically, we're using the pre-sum of ending with this one minus the pre-sum ending with here instead of this one. Okay, that's how this one works. At least if we do this minus 1. If we do like a 0, if you prefix a 0 to the pre-sum array here, this one's going to be a R plus 1 and then L, right? So which means we have to move the index to the right for both of these two. But in our case, remember, so we have so we have, like, let's say this is a 5, right? 5, 6, 6, 6, 6, 4, right? So let's say we have 6, this one. And when the 4 comes in, we're saying that this is our right boundary, right? But in reality, what we're trying to calculate, we're trying to calculate the let's say this one, they're already gone, this one, right? And then now we're processing this 6 here. When we process this 6 here, and the array we're trying to get is this one, right? And for this one, if we're trying to use this formula to calculate the range sum, we should do a pre-sum of this one, right? That's why we have, so the sum will be the pre-sum of r minus 1, because this one means ending with this one, which is the r minus 1, right? And for the left boundaries, in this case, happen to be the L, right? Because we're trying to get this one here, right? Ending with here, and ending with here is actually, if we do this one minus 1, it's exactly the L here. That's why we will need to do a pre-sum of L in this case. So a little bit like tricky to figure out the index in the pre-sum. Okay, and then let's do that, and we can simply calculate the answer in the end, right? So we have the answer dot current minimum times the sum. Okay, and then we append the current index into the increasing stack. So that's it, right? So we have a mod to 10 to the power of 9 plus 7, and then we return the answer modular mod. So that's it, right? If I run the code, pre-sum, this one. Okay. Yeah, there we go, right? So time complexity, right? I mean, n log n, right? N log n, we have a, oh no, sorry, it's not n log n. It's O of n actually. O of n. It's just like a monotonic stack here. Yeah, so just to recap, right? I mean, actually the idea to solve this problem is pretty important in my opinion. It's another like very classic use case for a monotonic stack, which is the every time. So the key idea for this problem is that we need to fix the number. We need to assuming this number will be the minimum number of this array, and we're trying to find a way to find the left and the right boundaries for array, right? For the longest array, who has this this number as the smallest number. And if we use a like monotonic stack here, so the moment the current number is smaller than this number, and then we know the right boundary is the index for the current number. And the only thing left is that how can we find the left boundaries, right? That's why we use like this increasing stack, because we know the next one in this increasing stack will be the left boundaries. Otherwise, because because any number who is greater than the current number has already been popped out from this increasing stack, right? So that's why in this it's increasing monotonic stack it's very good to find the next smaller number or the next greater number, in a sense, right? And then on top of that, we just do a pre-sum trick. And the last of the last is the few tricks to handle. So for example, to append a -1 to the numbers so that we can handle the last the remaining numbers in the monotonic stack. And to add like a -1 to this stack is because, if we have 2, 3, 4 left in the stack, right? So we'll have like the left boundaries for this one, because if we only have one number left in the stack, okay, for that case, actually, the left boundaries is -1 in this case. Basically, by adding this -1, we're assuming we are making sure there's always a left boundaries somewhere in this stack. Okay, and maybe one last time to go over this special case, right? For this 234 case, and about how can we use this -1, right? How this -1 will help us. So basically, let's say we have 2, 3, 8, 9, right? I mean 6, 4, 6, 4, 5, 6, 4. Yeah. So in this one, as you guys can see, so when the 4 comes in, all this thing will be gone, right? Basically, we have already calculated that. So in the end, we'll have like 2, 3, 4, 2, 3, 4 in the left in the increasing stack, and now we are adding like this -1, right? So that we can make sure we have taken care of all the numbers. So now, as you guys can see, so when the -1 comes in, the 4 will be popped out, and this is going to be the number, the minimum number we're trying to use here. And for the array who has the 4 as a minimum number, the right boundary is again is this one. It's the -1, which is this is the R. And the left boundary is what? It's this one. It's 3. It's this one. It's the left boundary. And that's exactly correct, right? Because so for the array whose smaller number, the longest array whose smaller minimum number is 4 is this one. That's why the left boundary is correct, right? That's why we pop this 4 out, and then when we pop 3 out, right? Again, the right boundary stays the same, right? Now the left boundary moves to here, right? Now 3 is out. In the end, 2 is out, right? So when 2 is out, the right boundary is still this one. How about the left boundary? That's why that's why we add this -1 into the increasing stack, because we'll have like the -1 at the beginning of the increasing stack. That's why the left is this one, okay? And that's why we have this pre-sum of -1 to help us to find the range sum, right? And the left will be -1, and we can find it's 0 for this -1 index in the pre-sum. That's how we find the range sum for 2 here, from this one to here. Yeah, I think that's pretty much everything I want to talk about for this problem. I know the monotonic stack is hard to understand, and it's hard to come up with, but I guess with enough of practice, and you should be able to get some extent of understanding, and when the scenarios we can utilize to a monotonic stack. Cool. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.